Up today was from the lab we did, the one with the cart rolling down the ramp, where you measured like GPE and KE and all that stuff. To the best of your ability, can you explain to me like the connection between GPE and KE? Like, what is the relationship of those two things? Is what I'm asking for here. You want to be on page number 50 is where you want to stick these notes. Your essential question today is, how is the law of conservation of energy related to this word we're going to learn today, mechanical energy? Your code is 220, so 4 questions from you, and your topic is other forms of energy. Starting with the notes today is just kind of reviewing what we've been doing, which is talking about potential and kinetic energy, because some of what we're doing today is combining those things. So it's important, again, to me, that you know GPE, that you know KE, and it would even be helpful if you had the formulas in your head, because on the test you're going to have the formulas in your head. So it'd be good if you could start thinking about remembering those things or having them set up in your head. So if we start with the next thing, I'm going to ask you 2 questions basically. And the first one is, what things does potential energy depend upon? Aurora? Height and mass. Those are the 2, right? The more mass you have, the more GPE you've got, the more height you've got, the more GPE you've got. So the only reason you'd need to write this down right here is if you did not know the same answer that Aurora just said. If you did not know that, then write this down. If you already had it and just didn't raise your hand, you don't need to write it. What's that? We're going to have some vocab today. So next question is same question, but kinetic energy. What things does kinetic energy depend on? Dante? Oh, you got one of them. You're 50%. Yes, ma'am. Mass and velocity are the 2. So same answer I had last time. If you didn't know what she just said, make sure you get that down. If you already knew it, then don't worry about it. Yes, Riley?
Can gravitational pull affect it too? Because like if it was like
yeah, absolutely. Yeah, it's just because, like, yes, you're right, is the answer. Yeah. Even though on Earth it's always the same, on other planets it's different, so yeah. Yeah, if you go, you know how it's like 9.8 meters per second squared? If you went up higher, like, and went out way more decimals, you'd start to see changes in those decimals, but it's not going to make a difference. Like, practically, it doesn't make a difference, if that makes sense. Technically, yes. Practically, not so much. So here are the 2 formulas. If you don't have them, you should have them on 2 different pages. So if you already have them, you definitely don't need to write these down a second or a third time. But if you didn't get them, there they are for you. 1/2 mv squared, where m is mass and v is velocity. And remember, the squared part comes first. And then in this one, as Dante, I think, pointed out when we took the quiz, I can just take 3 numbers and multiply them together, right? Yep, that's what you do for these 3 numbers. Doesn't matter the order. I've got it as MGH. Doesn't matter what order you have those in. And then you only need to remember one of those numbers. Which one of those numbers is one you got to have in your head? 9.8, and that's for gravity, right? Right, or any place other than Earth. Yes, Dante? Say that one more time. No, multiply.
No. Okay.
No, go ahead. And this is like a vocab for you, so if you're thinking about vocab, the vocab phrase would be the law of conservation of energy. And it's the same as every other conservation of law that's out there. There's the conservation of momentum, which says that momentum can't be destroyed or created, it can only be transformed. There's conservation of matter. Matter can't be created or destroyed, it can only be transformed. There's the law of this, the law of conservation of energy, which says that energy cannot be created and it cannot be destroyed, but it can be transformed. And so you can't make energy, you can't get rid of energy, but you can transform it from one thing to another. Say it one more time. Yeah. Yeah, you write it however you want. They're your notes. So I'm not going to ding you on that. You make them whatever you need to make them. And in fact, so moving on to the next one. Oh, sorry. Going back. I think going back. Something's happening wrong here. I know. I'm trying to get right there. And one more.
Problem solved.
Energy that are out there. And the one today that we're going to focus on, because it's got a formula to go with it, is called mechanical energy. So here's the next definition for you. Mechanical energy is the potential and the kinetic energy combined. And when you're talking about combining something, what math operation are you talking about? Addition, yeah. So we're talking about like potential energy added to kinetic energy, and you've got yourself mechanical energy. So I bet you, we could even come up with a formula for this, just knowing what the definition of it is. If it is the combination of potential and kinetic energy, how would we write that in a formula? Okay, so let's break those down. What's our formula for KE? So I heard like 1/2. Okay, so that's our KE part of it, right? Plus. Right, so that's what it looks like as a formula right there. This is probably not showing up on here. If I erase this, though. I don't know. It's not tracking up. I don't know what's going on. Look up, thing. Right there. There's the formulas you want. Okay. This thing is still struggling to keep up here. What is going on? There it goes. Yeah. Straight to your phone. So in any case, there's the formula we're going to work with, and I can make this make a little bit of sense up here too if we want to take a look at this. We can use either a half pipe like we're talking about here. You could use a roller coaster if you want to, but whatever. You guys actually have the same exact problem. You're just going to use actual numbers on your homework tonight. But let's take a look at it. If we've got, let's say, like Tim Culver, he's riding his skateboard, doing his thing, and he's getting ready to go up a half pipe here. Would you agree that this would be the lowest height Tim could be at on this half pipe? As a result of that, if that's as low as he can go, how much GPE would he have if that's as low as he can go? 0, right? So can you agree with me then that at the lowest height, Tim would have 0 GPE on there? Okay. Yeah. So next thing is that we know that GPE plus KE in this situation is going to be 100% of your energy, right? Like all your energy is going to be stored in that sense. So we know that that's going to be 100. So we know that 0 plus something's got to get you 100. Right? That means that at this point in time, all of Tim's energy is in the form of kinetic energy. Right? Tian? It's 100%. It's not a number. It's just like 100%. Those two things have to total up to 100% because that's all the energy. So if we look over here, man, what is going on with this thing today? It's not tracking. There it goes. So if we look at this and we consider that Tim is exactly halfway up the ramp here, would you agree that as he's gone up the ramp, he has slowed down, right? If he has slowed down, this number cannot be 100% anymore because he's lost some kinetic energy. We could do 50-50, right? We could say that he's got 50% KE, and since he's halfway up, he'd have 50% GPE, and you'd still have 100%, right? What if it was a little bit different than that? What if it wasn't 50-50? What if he had like 33% right there? How much GPE would he have? Close. Right? Because no matter what, when you add those two things together, they got to equal, whoops, not velocity is 100, but that's 100. No matter what, when you add those two things together, they're going to add up to 100% of your energy. So if this number, if we change this from percent to joules, right? No matter what, those things are going to add up to 100 joules or whatever the total amount of energy you have here. At the top of the ramp, up there, would you agree that just for a split second when you're at the top of one of those things, you stop before you come, you've got to like reverse direction. You go up, you stop, and then you come back down? So we're going to assume that this is the point where he is not moving at all. So if he's not moving at all, what percent of his energy would be kinetic? 0%, which would mean 100% would be right there, right? And what I'm trying to show you is no matter what, whatever point on here you're at, when you add these two things up, you should get your mechanical energy. Right? And it should always be 100%, should always be equal to like the full amount of energy. Subi?
Should it always be 100?
The answer, no. So this is totally just an example. So I confused the last class on that. I'm using percentages here rather than like actual numbers. So let me show you another way to think about this here. So we can solve a little bit of this down here, right? Do you guys have your calculators handy?
No.
Can you get a calculator handy or a phone? I'll give you a second. There's a drawer over there with them. Everybody got a calculator now? Anybody need a calculator? Doesn't have one out? Needs one? Bobby, you got yourself a calculator handy? Okay. You got one, Nathan? Okay, second drawer right there. Calculators are at. So, let me show you what I'm talking about here, and I can show you how to solve this stuff. If you've got your calculator out, we can make this work. Because we know to get GPE and KE, we've got the formulas form, right? So if you look right here on this thing, we've got mass and we've got velocity. Can we use those to calculate either GPE or KE? Which can we calculate with mass and velocity? All right. So we could figure out right here how much kinetic energy this person has. So let's do that. I'll do it up here. You guys can do it on your calculators, and we'll see if we come up with the same answer and stuff. But it should be mass, which is 60 times 8 squared over 2 by